In the southern summer of 1984, when I was still in high school, something unexpected caught my attention. In the window of a small bookstore near my home, there was a book. Its title was striking: The Fifth Generation: Artificial Intelligence and Japan's Computer Challenge to the World. At that moment, I already understood what generation meant. Computers had evolved through 4 generations: vacuum tubes, transistors, integrated circuits, and microprocessors, like the one we had at home where we learned BASIC. So I imagined something very technical. I expected diagrams, architecture, maybe even code, perhaps in Fortran, Lisp, or Prolog. I bought the book, and I was surprised. There were almost no diagrams, very little technical detail. Instead, it read like a warning. The book presented the Japanese project not just as innovation, but as a direct challenge to the technological leadership of the United States. The tone was urgent, almost dramatic, a wake-up call to governments and industries. Technology was no longer just engineering. It was a competition. It was a strategy. It was power. Years later, the project was labeled a failure, so much so that it almost became a taboo topic. But was it really a failure? Or was it misunderstood? Because behind that story, there are deeper lessons about technology, about politics, and about the paths we choose. Even though it was considered a failure, I will take many lessons from it and share them with you in this talk. Today, in this room, just like in 1981 during the launch of the Fifth Generation project, no one ignores that AI agents are opening a new era of automation. I think we can all say this with confidence. However, as you know, this transformation is not free of challenges. The issue is not the technology itself. The problem is how we use it. According to Gartner, more than 40% of AI agent projects will be canceled by 2027. And I don't want to start this talk on a negative note, but this is important to understand. Many of these projects are driven by hype. They lack clear business value. They are expensive, and very often they do not have a solid strategy to move into production. So the question is not whether AI agents will change the world. The question is, how do we make them work in the real world? We conducted a survey to understand how organizations describe the current state of agentic AI in their operations. What we found is very interesting. Most companies are in an intermediate stage. They are actively experimenting, and in many cases they are already implementing AI across different areas, but mainly in isolated use cases. As you can see, around 61% of respondents are in this situation. This tells us a lot about where we are today. Now, to be honest, when a client comes to us and says they want to implement AI, especially when their processes are still very manual or not clearly defined, my first reaction is not technical. It's more like a diagnosis. One of the first questions I ask is, where is your data? Because one key idea we must understand is this: AI amplifies whatever foundation it is built on, whether it is good or bad. So sometimes I tell our clients to think about AI as a multiplier. If you take a clean and well-defined process and you multiply it with AI, you get faster and better results. But if you take a broken or unclear process and you multiply it with AI, you just get chaos faster. So the real challenge is not only implementing AI, it is preparing the ground where AI will operate. What I want to emphasize is something very simple, but very important. We need to define the process clearly, and we need clean data. Now, I also want to be realistic. If you wait for your data to be perfect before starting with AI, you will wait for a very long time. So the goal is not perfection. The goal is direction. The good news is that in our industry, we already have a strong foundation. We have something very well studied and standardized, ISO 95, and the automation pyramid. In this model, data comes directly from the field. It is captured by SCADA systems. This is where everything starts. So if we think about agentic AI, this is our foundation. But here is the key point. We do not want a clippy version 2.0. We do not want a simple assistant on top of the system. We need something different. We need to rethink the architecture. SCADA systems should not just connect to AI. They should be designed as AI agents from the beginning. This means rethinking how data flows, how decisions are made, and how systems interact in real time. So again, the challenge is not only adding AI, it is redesigning the foundation where AI will live. Let's start by understanding how modern AI agents work and what role language models play in them. A language model, or LLM, generates a reasonable continuation of a text, one word at a time. By reasonable, we mean what we expect someone to write after being exposed to billions of web pages and texts. But here's the interesting part. If the model always chooses the most probable next word, the result becomes repetitive and eventually incoherent. And to be honest, we still do not fully understand why this happens. So how do we solve this? We use a parameter called temperature. Temperature controls how much randomness we allow in the selection of the next word. Instead of always picking the top option, the model can explore other likely options. In modern models, values around 0.8 usually produce text that is both coherent and natural. So in simple terms, temperature helps the model balance between being predictable and being creative. Where do these probabilities come from? At the beginning, predictors were simple statistical models. They estimated the probability of the next letter based on previous letters, and later based on word patterns. With this, or with trained models, it was possible to guess the word being written. In the 2000s, we started to see this in real applications like Gmail, suggesting the next word as we type. These systems were based on models like RNNs or LSTMs. They convert words into vectors and compare them by similarity. This was an improvement, but they could only predict the next word, and they had very limited understanding of the full context. After the paper Attention is All You Need was published in 2017, language models changed in a fundamental way. The transformer introduced a new idea: attention. Instead of reading text in order, the model can look at all words simultaneously and decide which are important. This brought several advantages. First, models became much faster to train. Second, they could better understand long-range dependencies. And third, they scaled more easily with greater data and computing resources. Because of this, transformers became the foundation of modern language models like GPT and BERT. In short, this paper did not just improve language models, it changed the entire paradigm of how machines understand and generate language. Today I want to explain a simple question. How does a large language model reason? The short answer is, it does not really reason. A large language model is trained on a huge amount of text. Inside that data, it captures thousands of explanations, demonstrations, and logical steps. For example, it learns patterns like if A implies B and B implies C, then C. But it does not understand formal logic. It only imitates how reasoning is expressed in language. In this sense, these models are a modern example of the Chinese room proposed by John Searle Faples. They do not truly understand, but they can simulate reasoning very effectively. At the same time, research like emergent abilities of large language models from 2022 suggests that some capabilities are not present in small models, but suddenly appear in larger ones. Because of this, researchers like Geoffrey Hinton, who received the Nobel Prize, warn us about the risks of artificial intelligence. And as an engineer might say, it does not matter if it thinks, it solves the problem as if it did. LLM agent. Now let's imagine we have a large language model that can simulate reasoning. If we take this model, and in addition to the user's question we provide a description of the tools it can use, then something interesting happens. The model can decide not only what to answer, but also which tools to call in order to build that answer. In practice, we can run the LLM in a loop. At each step, the model analyzes the problem, selects a tool, executes it, and then uses the result as new context. This process can be done sequentially or even in parallel until the model reaches a final answer. But we can go even further. We can enrich the input of the model with domain knowledge, for example, operation and maintenance manuals of a production line. By doing this, the answers become more precise, more grounded, and more useful for real industrial scenarios. And finally, we can add short-term memory. This allows the model to remember previous questions and answers in the conversation, creating continuity and context over time. So, with tools, knowledge, and memory, we have what we call an LLM agent. At first glance, this architecture works very well. It is powerful, flexible, and ideal for building prototypes. However, it has a fundamental limitation. Large language models have a restricted input size. In other words, there is a maximum number of tokens that the model can process at once. This means that as we keep adding more information, the user question, the tool descriptions, the manuals, and the conversation history, we quickly reach that limit. And when that happens, the model does not fail in an obvious way. Instead, it silently ignores part of the input. So the model may miss critical information, and then it fills the gaps by generating plausible but incorrect content. In other words, it starts to hallucinate. That is why this architecture, as it is, works well for prototypes, but is not enough for a production system. To move to production, we need better strategies to manage context, control what the model sees, and ensure that the information it uses is always relevant and reliable. What is missing? Now it is time to go back to one of the two key diagrams I mentioned at the beginning of this talk. That diagram was presented almost 40 years ago in Tokyo, and today, if we look at it again, something interesting happens. Many of its components can now be implemented using the agent architecture we discussed in the previous slide. For example, the system can coordinate tools, manage context, and generate responses. But there is still a critical piece that we need to improve: reliable logical reasoning. This is where recent work like Logic-LM becomes very important. Logic-LM is a 2023 research approach that combines large language models with symbolic solvers. The idea is simple but powerful. First, the LLM translates a natural language problem into formal logic. Then, a deterministic solver performs the reasoning and verifies the result. Finally, the system can use feedback from the solver to refine the answer. By doing this, we separate language from logic, and as a result, we get much more accurate and trustworthy reasoning. This approach brings us closer to what we traditionally call an expert system. An expert system does not only reason, it also has a knowledge base. And this is another key element that is still missing in many modern LLM architectures. Knowledge bases are not exactly the same as LLMs. In academia, they are often related to semantic information retrieval systems. These systems allow us to store large amounts of structured and unstructured knowledge and retrieve only what is relevant at a given moment. And this is very important because it helps us solve one of the biggest limitations of LLMs: the token limit. A language model cannot read everything at once, but humans cannot either. When we think about human memory, we realize that it is not exhaustive. It is selective. We do not scan all our memories. We retrieve the ones that are relevant to the current context. So if we want to build truly intelligent agents, we need to replicate this behavior. The agent should have mechanisms to retrieve only the information that matters for the current conversation. This includes short-term memory to keep track of the dialogue, relevant sections of manuals and documents, and even the description of tools, including their parameters and functionality, but only the tools that are actually needed. In this way, we move from a system that tries to load everything to a system that knows what to load and when. Quantum agent. At this point, we can bring everything together. All the components and technologies we discussed can now be combined into a single agent-based system, ready to be deployed in production. We call this architecture the quantum agent. The main objective of these improvements is simple, but very important. Open quote, to retrieve only the relevant information from the user's prompt, and to provide the minimum necessary context to generate a correct answer. Close quote. To achieve this, we need to organize knowledge in a smarter way. We store different types of information in a central knowledge base: short-term memory from the conversation, operation and maintenance manuals of the production line, and the specification of the SCADA interface. All this information is structured and stored as a knowledge graph. Now, before the main agent starts reasoning, we introduce a specialized component, a semantic retrieval system. This is an intelligent agent, independent from the main one. Its job is to search and select the most relevant pieces of information for the current question. To do this, it uses three types of models: embeddings to represent meaning, re-ranking models to improve relevance, and a large language model to refine the selection. In the first step, this retrieval agent analyzes the user's question and extracts the most relevant context from the knowledge base. Then, this selected context is injected into the prompt of the main agent. So, instead of sending everything to the model, we send only what matters. This approach is inspired by Retrieval-Augmented Generation but extended. In our case, RAG is not limited to documents. It supports all components that are part of the system's context: memory, manuals, and even tool descriptions. But there is another important piece. To make this system work, we need a process that reads the documentation, for example, maintenance and operation manuals, and converts it into structured knowledge. This process transforms unstructured text into a knowledge graph, which can then be stored and efficiently queried. So the system is not only retrieving text, it is retrieving structured understanding. In summary, the retrieval agent finds the right information, the knowledge graph organizes it, and the main agent uses it to generate the answer. This is what allows us to move from a simple prototype to a scalable, reliable, and production-ready intelligent system. Implementation. This architecture is the core of the Quantum Industrial Studio. We have redesigned the traditional SCADA system so that it behaves like an intelligent agent. Instead of only displaying data, the system can now understand questions and actively help solve problems. It can handle simple tasks, like finding the correlation between different signals, but it can also perform much more complex operations. For example, it can process historical and real-time data and create new signals using advanced filters. This means it can combine, transform, and analyze data in ways that were not possible before. In this new approach, the SCADA system is no longer just a monitoring tool. It becomes an intelligent assistant for engineers and operators. It can explore data, generate insights, and support decision-making in real time. In short, we move from passive visualization to active intelligence. If you would like to see agent-based automation in action, we have several related talks available. One of them shows how we work with time series using intelligent agents. We also have 2 additional talks where we explain how specific predictive maintenance problems were solved using the quantum agent. The time series session unfortunately overlaps with this talk, but if you are interested, please feel free to contact us. We will be happy to repeat the session for you. We believe these examples show how this technology can move from theory into real industrial applications. I hope this presentation has been useful. Thank you very much for your time and attention.